Okay, so we didn't get to do very much talking about GoldVarb on Thursday, so what I wanted to do today is to resume where we left it. Basically, if I remember correctly, we had done a no recode, and I had identified some of the problems, and I started telling you about the solutions that you should adopt, because if you do have problems, oh, and that's right, another question. So did you get the message about the document by Brian Hossein that I made available? So I think that's a very useful document that you may want to look at. In addition to the manual that is available online. So that's something else. So on the GoldVarb site, there is a manual that you can look at. All right, so what I want to resume then is looking at some of these problems. What are the solutions? Run an analysis and try, and look at the numbers actually, and because there are lots of numbers that come out of a GoldVarb analysis and give you a sense of what they can tell you, and hopefully also show you about cross tabulations, which is a very useful tool for finding skewing in your data, that is imbalances, and we're dealing with, most of us are dealing with data from conversations. So there's likely to be imbalances, and that's something we need to be aware of. And another very crucial topic that I have discussed on various occasions, but something we need to watch out for, is interaction. That is, when we have two different factors, which when you combine them, produce a result that is not the result that you expect. So either you get way more of one variant than you expect, or you get way less, but not what you expect from combining A and B. So that's the plan for today. But before I keep going, I want to ask you if you have any questions about what we did on Thursday. If there was anything that I went over too quickly, elements I didn't take the time to explain, or no? It's already too far back. All right, so to refresh your memory then, so what we did, so we generated some cells using a data file, using a condition file that is very simple. So basically it's all the factor groups, the variables that we code for, the first of which is your R-dependent variable. So in my case, it's whether or not appendices has taken place. And what we get is basically the distribution of the data. And what is really crucial for us is that there should be variable for each of the variants that we code for, because if there is no variable, we get something that we call a knockout, and that cannot be fed into the analysis. Right, rings a bell? So before looking at this some more, so what are all these numbers that we get? So here, so we have one factor group, and this factor group, if you look at my coding system, is the word type. So G is a grammatical politicized monosyllable, H is a grammatical non-politicized monosyllable, V is a verb and its preverbal clitics, L is a lexical monosyllable, and D is a polysyllabic word. So here what we see that, first of all, so we don't have knockout. So we're in good shape. We can feed all this stuff into GoldVarb. But what are all these numbers? So first, if we go across, so we have G, so that's a grammatical politicized monosyllable. So the first line is the number of tokens. So what this tells us is that we have 380 tokens of G. I will say G rather than repeating the whole thing all the time. 139 of these, or 36.6 of these, have appendices. and 241 of them, or 63.4% of these, don't have a parenthesis. All right? And then the last percentage we have here is the percentage of the 717 tokens. So out of 717 tokens in my sample, 53% of them are G. So that's skewing in the data already. So if we had equal distributions, we would expect about 20% in each category, right? But we see that G is way more common than the other ones. Something to keep in mind as you do your analysis. Then for H, so here we have far fewer tokens. We have only 15 of them, right? And 20% of those 15 or 3 tokens have a parenthesis, and 12 or 80% don't have a parenthesis. So that's what the numbers mean. And these 15 tokens represent only 2.1% of my 717 tokens. All right? So now that we know what these numbers mean, so we can go down quickly because we've done this before. And if you remember, so we have a problem when we get to factor group 7. Oh, and here, so why do we have 7 and then 8 between parentheses? Ali, you know? Mm-hmm.
Well, the first thing that you entered was the
dependent variable.
Yeah.
That's okay. That's very confusing.
So that one's not being looked at. It isn't represented with numbers, I guess. It's the 7th group of numbers, but you actually entered it as the 8th.
Right. Mm-hmm. So 8 is your original number, but in this analysis, it is number 7. And actually, when you do cross tabulations, then the number you have to use is 7. 8 won't be the right variable. So that is confusing, but that's something to keep in mind. So remember, we talked about, so this factor group is, so if we have, so remember, so what we look at is contexts where we have sequences, well, actually, here that can be, it is something, so it can be a vowel, it can be a consonant, or it can be nothing. We have 2 consonants that are not a possible onset, so if we have something like m, for example, or p, so that's a context for a parenthesis. And what factor group 8 is what kind of consonant this is. And what we saw on Thursday is that all 5 tokens that are a problem are tokens of the word rien. So where we have the semi-vowel y. So what should we do here with these tokens? We cannot feed them into the GoldVarb analysis. In this case, and we discussed whether we could group them with something else, and we decided that we can't because even though a glide and a liquid are phonologically pretty similar, we see that they behave very differently, right? So the glide categorically triggers a parenthesis, whereas a liquid does so only 20% of the time. So we can't group them. In this case, the best solution is really to exclude these tokens from the analysis. How do we do this? Actually, GoldVarb gives us a pretty simple way of doing this. I didn't show this, did I? Or I did? Mm-hmm. Basically, so, and actually I will do it because I want to run the analysis correctly. So we can do a find, so Control F, that will get me what I want. So we can look for the value G in column 8. So here it finds it. And if we want to eliminate these tokens from the analysis, we can simply delete them. And then we can find the next one. And, oops, I just want to delete this one. So we can delete all 5 tokens. Find the next one. And then the last one. And then I can save this as either under the same name or as a different name. So I can save it as without. So data appendices without rien. So when I look at my file name, I know what it is, and I know that this is the file that I want to use. So, and then the other factor group that we had a problem with is the syntactic coding, right? And I told you I tried to code for too many things, and it didn't really make sense. So here, the easiest is really to exclude it from the analysis. And that's what I did in my work. That's something we can do very easily. Yes, I do have the condition file. So here, for example, so this is factor group 12. So we can simply go here and delete it. And that factor will be ignored by GoldVarb. If the recoding we need to do is this simple, there's no use really to using the whole recode window and function, because it is user-friendly, but we don't need it to do something like this. So we can simply do it here. And we can always save this. So we can call it condition without syntax .cdn. Now, do we need to put? So, and that will be the recoding. But let's imagine we really want to do some recoding. Let's imagine, for example, that for the factor group 3, well, what used to be 4, what is now 3. So this is the preceding segment. So what comes before the side for appendices. So here what I have done is I have coded for, vowel, fricative, liquid, stop, nasal, glide, and nothing. I suspect that what kind of consonant we have doesn't really make a difference. That maybe what makes more sense is to just contrast a vowel versus a consonant versus nothing. So I can very, very easily recode by using the recode setup. And unless you're good at programming or figuring out this pretty simple language, I recommend that you use this recode window. So how do we go about it? So I think it is fairly self-explanatory, but so basically if we want to include a factor group, oh yeah, when I click on it you don't see the characters anymore, but so it is my dependent variable, right? So with O and E, so obviously this is something that I want to keep. So I select it, I select the whole line, and I copy it. Similarly for the second and the third, and you can use the shift key to select more than one at a time, and you simply copy them. So here you're not making any changes. Factor group 4 is the one that I want to recode for. So here I select the group, and I select recode, and I type in the new values. And the tricky thing here is that you really have to type in a value for each of the factors. So if you want to keep it the same, so if I want V to remain V, for example, I have to retype V. But then if I want F to become C for consonant, let's say, then I need to do that. So V remains V. F, I want to become C, so that C for consonant. Liquid becomes C for consonant. Stop becomes C for consonant. N becomes C. G becomes C. I could decide to keep it different, but I have decided to code it as C. And 0, nothing, I want to keep different. So here I type 0 again. And I have recoded my factor group. All right? Then the next factor group, so there were no problems with them. So I can just select them all and copy them, and they are copied as such. Then 12, that's the factor group that has all these knockouts that I want to keep. 13, I want to keep. And 14, I will keep. And I will explain to you why I'm not, actually I will show you why I'm not copying 15, why I'm leaving it out. So that, I'm done recoding. And so here, if we go to the condition window, we see the recoding that we have done. So we see that, so to the left, we have the new values. Well, so we see we have only V, C, and 0. To the right, we have the old values, so we can make sure we made no mistakes. And we see that 12 is left out, so that problem is solved. And that should generate a sample that we can feed into Varble. All right? So why did I exclude the last factor group that I coded for? So let's look at this. So let's look at factors group 13 and 14. What do you see here? That should make you suspicious. Anyone? Allie?
I guess it seems that the numbers for like C and 13 and W and 14 are the same, and G and D are also the same, so they're potentially the exact same tokens.
Potentially what, right?
The exact same tokens.
Exactly. So what these factor groups are speaker and village. I have only 2 speakers in this subsample because I wanted to have a sample that was smaller that wouldn't take a half hour to run. So one speaker is one from village and the other speaker is from another village. So there's complete overlap. And what happens actually if you try and run Varble with both of them is that it will run, but it produces 2 different models because it can't decide which one it is, right? Because both are identical. So here, let's just avoid the problem and run it by excluding 14. And when I have more speakers, then it makes sense to code for both speaker and village. But in this case, it didn't. All right? Okay, so we have some tokens. We have a condition file. So now, what do we need to do? Has anyone tried to play with the program, or does anyone remember what we do after we have recorded our data? Sorry?
Save it.
Yeah, we should save. That's true. So that's always a good idea. And here, so we could save it, for example, and call it condition vowel consonant, something like that. So something that makes sense to you. And so that's always a good idea. After saving it, what do? We have to load cells to memory. So we have already, so that's really what GoldVarb uses. And here it tells you already have cells in memory. Do you want to save them? You can save them if you want, but I tend not to save them. So I say I don't want them. Wait, what happened?
Yes, you want to discard them.
Yeah.
You want to just save them.
Sorry?
It says, do you want to discard them, not do you want to save
Ah,
them?
okay. Oh, yeah. So maybe if I read, yes, I want to discard them, and I want to create cells from the data and conditions that are open on screen, yes. Do I want to save my, this is where I don't save, right? And here I have to pick my application values, so E for appendices. So my cells have been created, so I have to go through them and see if I have any of those warning labels. No knockout, no singleton. Oh, did I say what a singleton is? A singleton is instances where you have only one token. So then that can't be variation, right? So it can't be fed into GoldVarb. So either you regroup, you group with another value, or you exclude and you say, well, I don't have enough data, I cannot look at it, but that's another warning label. Okay, so we have no knockouts, no singletons, so we're in good shape, and we can run the analysis. So now what we need to do is a binomial up and down analysis. So that will go on for a few seconds. So what does GoldVarb try to do here? So it looks at all of my 717 tokens, and it tries to determine which of the linguistic and social factors I have coded for have a significant effect on whether appendices takes place or not. And it tries to do it in two different ways. It tries to do it first by building up a model that is more and more complex. So it looks first at a model in which none of my variables is included. And it determines how well it fits the data. Then it tries adding one variable and to try to and see if it produces a model that is significantly better than the model with no variables. And it looks at every single variable independently, and it picks the one that best improves the model. It keeps that variable, and then it tries adding a second one. And again, it tries with everyone in turn, and it tries to see if it can produce a model with two variables that is significantly better than the best model with only one variable. And it does this by adding variables for as long as it gets models that are significantly better than the simpler models. When it can no longer do it, then it stops. And it says, this is the best model I can build. Then in the step-down analysis, it does the opposite. It starts out with a model where all of the variables are included. It sees how well it accounts for the data, and it tries removing one factor group, one variable. And if by removing the variable, it produces a model that is not significantly worse than the more complex model, then this is good, right? Because we want the simplest model that can account for the data. There's no use in keeping factor groups that, yeah, we know, so that don't improve the model. So that's the general procedure. Does it make sense? Okay. So GoldVarb has finished running, and these new versions are actually very nice to use. It actually tells you where you can find the best models in the stepping up run and in the stepping down run. And one thing you want to do is you want to compare those two models and make sure that they're the same. But before we get there, so let's look at this all these data that the program generates. So this is where the probabilistic analysis starts. So what we have at level 0 is its analysis where no factor group, no variable is included. And the log likelihood is a measure of how well the model fits the data. It's a negative value. So the further away, the bigger the number, the less good it is. So what GoldVarb tries to do is to build a model where this value gets as close to 0 as possible. So that's our initial number. So then, it tries adding the factor group 2, and we see that the log likelihood goes up a little bit. So, right? So from minus 457 to minus 455. But the improvement is not significant. It is above this 0.05 threshold that we use. So it won't keep this. Then it tries factor group 2 here. And we see that, well, it's actually less good than the previous one, even though it's better than the original one, and it is not significant. So not good. Then, if we move on to factor group 3, we see that there's a big improvement, right? We go from negative 457 to negative 389, and it is a significant improvement. But is it the best improvement? So GoldVarb, and I won't do this for all the factor groups, but it keeps doing the same exercise, looking at each factor group independently. And in the end, no, you can't read that if I do this. Factor group 3 was the best improvement. So it retains it with its factors, and then at level 2, it will try adding factor group 1, then 2, then 3, 4, and try to determine where the best improvement is. So here, so here for factor group 3, here, so we had 389 negative for the log likelihood. So then if we add factor group 3, so 387, it is slightly better, but not significant. If we go on with factor group 2, so with 3, so that's not better. So and then factor group 4, we have a p-value. Why am I here? Of 586. That's not significant. Factor group 5. So here we have a pretty nice improvement. Where am I? Here. And it is significant. It keeps doing it till it has tried with all factor groups, and factor group 5 is the one that produces the best improvement. So now we have factor group 1, 3, we have factor group 5. So can we add one more? So level 3, it tries building a model with 3 factor groups, and it finds that adding group 7 produces a significant improvement. So can we have a system with 4 factor groups? Yes. Factor group 12, when it is added to the model, produces a model that is significantly better. Can we have a model with 5? Yeah. So factor group 10 produces a significantly better model. But then we can't, if we try with 6 factor groups, it doesn't produce a model that is any better. So it stops there, and it tells you that the best model it's been able to build up is the model in run 50, in which we have factor groups 3, 5, 7, 12, and 10. And, oh, this is another improvement of the program. Now it tells you the order in which the factor groups have been selected. In the previous version, they were just a numerical order, so you had to go back through the whole thing to figure out which is the most significant. Chelsea?
So what that means is that groups 3, 5, 7, 12, and 10 all created together the most appendices, or?
So the model that takes all of these factor groups into account is best able to predict whether appendices takes place or not. Because so all of these factor groups, so for example, one of them is gemination. So if you do have a geminate, it favors appendices, but if you don't, it disfavors appendices. So whether you favor appendices or not depends on the variance within each variable. But it's really trying to make the best probabilistic prediction. Ali?
And just to, I guess, ask this again. So group number 3 was actually the 4th, letter. In your
Right.
word.
So in my coding system, then that's the preceding phonological environment.
Okay.
So whether you have a vowel or consonant or nothing. Yeah. Yeah, that's right. So VC0, exactly. All right. Okay, so let's look at step down. Then, actually, maybe before we do that, I will just extract model the run 50. So copy it to a word processor here, so that we can compare them easily. I didn't copy it. Okay, here we go. So we'll come back to this. Okay, so starting at step down. So as I told you, so this time we try out first with all factor groups and how well does it account for the data. So we see it accounts for the data better than if we had no factor groups at all. But do we really need all of this information? Is there anything that we can leave out without making the model worse? So it tries again. So here in the first run, it leaves out factor group 2. And we see that the log likelihood increases a little bit. But this is not a significant difference. So leaving out factor group 1 doesn't really harm the model. But is that the one whose harmlessness is the greatest? Is that the first one we should exclude? So then it looks at factor group 2, and so it's a model that is not significantly worse. And then it looks at factor group 3. So here, if we leave factor group 3 out, we get a significant change. So we don't want to do that. And the log likelihood is bigger than it was with all factor groups. So we won't want to throw this factor group out. And then it tries with 4, 5, and everything. And at the end of this level, so it has determined that factor group 4 is the one that is the most useless in trying to predict the variation. So kick it out and see if there's anything else that can be kicked out. So it does the same exercise again, and at the end of the level, it determines that factor group 2 is also useless. So let's kick it out and keep doing this until there are no factor groups that we can kick out. So factor group 8 could be kicked out. until there's nothing else that we can kick out without and maintain the quality, the goodness of it. So yeah. So here we see, so in the last level, anything that we try to exclude produces a significant difference. So significant 0, 0, 0, 14, 0, 25, 0, 10. So we can't exclude any of them. So what can be eliminated is factor groups 2, 4, 2, 8, 1, 6, 9, 11, which are all factor groups that were not kept in the building up of the model, right? And it tells us that the best model in the stepping down run is 121. So let's find 121. Let's copy it so we can compare it with model 50. So here we have our two models. So we see that the factor groups that have been added are 3, 5, 7, 10, and 12. And the ones that have been retained are 3, 5, 7, 10, and 12. It's the same factor groups. And if we look at the weight for each variant, we see that they're also the same. So whether we're looking at, so a preceding vowel disfavors appendices with a probability of 31%. A preceding consonant favors appendices with a probability of 78.7%. And a preceding nothing slightly favors appendices with a probability of 50%, 55%. So we have convergence. Whether we go at it by trying to build a model or deconstruct a model, we get the same result. So we can feel very confident about our results. So we have all these numbers, but in the end, these are the ones that we need to deal with. These are the ones, and actually, since they're the same, we don't need both of them. So what will be converted into a result file in your term paper or in your publication is these numbers. Obviously, they have to be spelled out, right? Because that's something that is meaningless to a reader. But so that's what will turn into a table like, actually, a table like this. So the numbers in the Word file I had, they're the numbers here. And these numbers that are earlier in the file are also very important because you need to include them so that the readers know how much data you're looking at. Because sometimes when you get surprising data results, it's because you don't have enough tokens. So for example, here, if I look at the examples of a glide, so in the general analysis, I did keep them because there was variation. But you see, I have only 12 tokens. Whereas if we're looking at examples where there's a stop, I had 853 tokens. So if there's something surprising about a glide, it could be because I don't have quite enough data. But it is very important to provide all of these data in your analysis. And the order in which I present the factor groups is the order in which they are selected. So what I'm saying is what I said earlier, is that the factor group that has the most power in predicting whether appendices takes place or not is what comes before. Is it a vowel or is it a consonant? So this was at the inside of an utterance, so nothing was not a possibility. It was only a choice between consonant and vowel. Ali?
Okay, can you explain to me the differences between like the 0.84 and then 80%? Like what are...
Right. Mm-hmm. So why do we need both? Because actually if we look at this, you know, the numbers are very close, right? They're not like, for a preceding vowel, it's identical. But for preceding consonant, it's different. And sometimes it can be quite different. For example, here if we look at pronominal clitics plus verb, so if we look at the actual data, we see that appendices took place 45% of the time. But GoldVarb has a probability of 60. Why is this possible? It's possible, and actually that goes to the heart of why we go beyond doing frequencies and we do probabilities. And the core of this, the core element of this is that in sociolinguistics, our data tend to be very skewed. Things are not equally distributed. So it's quite possible, for example, that some phonological environments are more common than others. Or in this case, what happens is that GoldVarb determined that actually the amount of appendices that we observe in the corpus doesn't reflect how well is lower. I'm trying to find the best way to explain this. Actually, so GoldVarb decided that the actual frequency of appendices for pronominal clitics is lower than it should be. Because one characteristic of pronominal clitics is that almost all of them are fricatives. And fricatives disfavor appendices. So GoldVarb has decided that if pronominal clitics started with were equally distributed across all the different kinds of consonants, then we would see more appendices than we actually see in the corpus. So I don't know to what extent my colleagues agree with me, but one comparison, one parallel often draw between percentages and probabilities is that it's parallel to some extent to, I said percentages first, so performance and competence. All kinds of things can happen in performance, right? We can be tired, we can be trying to express a very complex idea, we can be obsessed about an idea and talk only about this, so we may not show people that we know all of these other words. All of this can happen. But GoldVarb tries to go beyond this performance to see what the actual linguistic competence is behind these data. So what does it mean for the difference between a consonant? Well, GoldVarb determines that the favoring effect of consonants is actually a bit more than what we can see in the data. Did that make sense? I know many people in linguistics don't like numbers very much. And I was talking about simplicity. Why would we want to build a more complex system or model than we need to? So why would we want to use probability when percentages can do the job? Well, that's the thing. Percentages don't always do the job. So that's why we have to use a more complex program. Other questions about all of this? No? Let's see, let me look at them because time is going very quickly. Yeah, Ali?
Okay. Earlier, when you took out all
So thanks for asking the question, because in previous discussions of GoldVarb, actually, I would use a slash for rien, but I would tell people don't do it because that's not quite so the right solution. You have to think about your hypotheses, about what's behind. So in this case, because with rien there's never any variation, so telling the program to ignore these 5 tokens of rien for this factor group, that's kind of cheating. So we really have to exclude it and talk about it qualitatively. I use slash, for example, do I have it in? Oh, I didn't do it right in the document I gave you. But if you have my code in system, if you look at factor group 5 for the preceding phonological environment, place of articulation, in the document I gave you, I have 0 for non-applicable, vowel or nothing. There, I should have a slash. What the slash says is that the token as a whole is still relevant. It's still something I want to submit to analysis. But place for vowels or nothing is not a relevant category and not a relevant variable. So here, when you try to determine whether place of the preceding segment significantly influences appendices or not, do so by ignoring these tokens. And actually, if we go back a little bit, and I think here I did it right. So that will be. Yeah, oh yeah, that's right. Sorry. I did it right. So factor group 5, that's become 4. Look at the number of tokens. I have only 237 tokens here instead of 712. So all the tokens where I had a previous vowel or nothing have been excluded for this variable, not for the others. So that's the right place to do it. All right? Other questions? In the, 6 minutes I have left, so the last thing I want to do is to show you how to do a cross-tabulation and why this is useful. So in the cell menu, you have the option of cross-tabulation. And so here, if you suspect that your data may be skewed, unevenly distributed, or there may be interaction, by doing a cross-tabulation of these 2 factor groups, that's a good way to test. So let's here do a cross-tabulation for 3, for example, which is the preceding phonological environment, and 12, which is the speaker, if I remember correctly. Yes, that's what it is. So I have only 2 speakers, C and G. But remember, I've repeated you many times, you can't combine pears and apples and oranges. If they behave differently, then maybe you have to look at them differently. So we saw that overall, a preceding vowel disfavors appendices, a preceding consonant favors appendices, and nothing has a slightly favorable effect. So, but is it the same case, the same for both speakers? So here, if we look at, so these are the speakers, right, C and G. These are the phonological contexts. And once again, lots of numbers. So the first line is your application value. So the cases where you have appendices. So for C, you have 42 tokens following a vowel. and you have where you have appendices, you have 126 where you don't have appendices, so the non-application value, for a total of 168 tokens, or a rate of appendices of 25%. All right? And if we look at G, we see that the numbers are a bit different. So he has only 11% appendices and 89% appendices. But we see that both speakers more often don't have appendices than they have appendices after a vowel. And if we compare with what happens after a consonant, here we see that the rate of appendices is much higher. So whereas C has only 25% appendices after a vowel, he has 61% appendices after a consonant. G has 11% after a vowel and 62% after a consonant. Actually, here the numbers are amazingly similar, right? So after a consonant, they behave very similarly. And then here, I just saw this. One thing that is strange is that G apparently has no tokens at all, following nothing, which I have to look into. I'm a bit suspicious of this, so here we can't compare. But we see that the favoring effect of a nothing is higher than for vowel, and is in between vowel and consonant, which is what we saw for the whole population. So what we see here is that there are some quantitative differences across our two speakers, between our two speakers, but there are very similar trends. If we had seen a reversal, then we might have to divide our sample and do some independent analyses. Questions about this? Lots of numbers, right? But at least once you know what they represent, so it's not too difficult. You have to keep track. And what you must never forget is what your application value is. So that's what the percentages are interpreted against. All right? So we will be discussing the phonological variation analysis.